All right, physics. So we've gotten a chance to kind of look at this lab and do the different pieces of this lab. You had the part with the tape and the paper and the foil. Um, you should have gotten a chance to do the thing with the PVC pipe, which was hopefully like showed like a stronger version of the tape. I know that like not everybody's able to see it during class because real life conditions are finicky. But you know, I talked about. Hopefully, I talked about this during class. If you're watching this and you're fully remote, I'm going to be explaining some stuff. Um, so hopefully, you watched the last video where we started talking about how to how to go through this. You have the tape that you pull apart, and you kind of hold it up, and someone else holds it up, and you see like, do they repel? Do they attract? Do they do this? So here's like, right, what should have happened. Now, if your lab didn't show this, don't say this, right? Your lab should report your results. Just because your lab isn't perfect doesn't mean you didn't do your lab correctly. It just means that lab conditions are non-ideal conditions, and like, it is what it is sometimes. But what should have happened was that, at least for the top part, the top and top should, oh goodness, nope, need the, that's not, that's wrong. How's that? Top and top should have repelled. This should have attracted. This should have attracted. This should have attracted. This was attract, repel, attract, attract. The foil was attract, should have been attract, attract, nothing, nothing. And paper should have been attract, attract, nothing, nothing. And that should kind of make sense based on what we talked about before, with respect to the top having one charge, the bottom having an opposite charge. So top and top should have the same charge. They should repel each other. Top and bottom have opposite charges. They should attract each other. And charged objects will always attract neutral objects. And the reason for that is we create this distribution of charge. So we're not affecting, and that's what happens on a bigger level. This section was with the tape. This section was with the PVC. This was like a very clear attraction here. All those were attract. Oh goodness. Let me think. The plastic. I think. I'm trying to remember what I did in class now. I think it was attract, repel, repel, attract. I think that's what it's supposed to be, but I don't remember exactly. It's been a minute. But use it with the PVC pipe. What you should have definitely noticed with the PVC is that the attraction and the repulsion was like way stronger, and that should kind of make sense. It's a bigger object than the tape, right? What was actually happening here? What physically was happening, right? So I'm going to talk about this kind of like, especially, ooh, hello? One day, my program will respond the first time. I don't know when that'll be. Or the third time, even, maybe? I'm going to talk about this kind of with respect to this electrostatic force, because I'm going to talk about the equation here, and I'm going to give you some questions. There'll be some questions in an assignment that'll be on my CBA. Also, the concepts today and the equation are both going to be on a quiz that will take place on Friday. So regardless of letter day, it's going to happen on Friday. It'll be an online quiz. Everyone will take it online. Hopefully my CBA doesn't crash. We'll find out together, right? But what we're looking at with that PVC pipe, which again slightly bigger. It was hollow. I'm just gonna draw it as a stick because that's easier. So here's the PVC pipe, and if you charged it, right? If you charged it with the, let's say, oh, it's in the lab actually. When you charged it with the fur becomes positive, and the PVC pipe will be negative. So it's cool, super cool. I appreciate you, computer. Please, there we go. Oh, too much? There we go. So this pipe just has a ton of extra electrons, which I'm just going to draw as a bunch of extra negative charges, right? What ends up happening when it comes near something neutral, like, I don't know, a piece of paper. I'm going to blow this up. Let's let's do this. So here's the piece of paper. It's neutral. So it has equal amounts of positive and negative. And for argument's sake, I'm just going to say it has 5 positives and it has 5 negatives, because that's simplifying things a little bit here. As I bring the paper close to the negatively charged object, the negatively charged PVC pipe, these negative charges, because they're loose, are going to move. Right? So the positive... I have to redraw this, apparently. The positive charges will have stayed put. And the negative charges are all going to run away. They all still exist. They're all still there. I haven't touched them together. I haven't changed the... I haven't actually changed anything. But because negative charges repel and electrons are mobile, they're able to move, even if not easily, right? Paper is not a good conductor, but if you try hard enough. The electrons get pushed away, which means now this negative object looks at something that is electrically neutral. It has 5 positives and 5 negatives. But now it actually will attract it, because it sees mostly positive charges close by. It does recognize there are negative charges, but they're kind of far away. Because they're far away, because the positive charges are close, the neutral object will have this distribution of charge, where suddenly part of it is positive and part of it is negative, and it's almost like it has poles. Last year in chemistry we talked about this with polar molecules and creating a dipole. Sorry guys, they're not going anywhere. All sciences are related. Sorry. But this is how you create a dipole, or a temporary dipole, because the second I take that PVC pipe away, these electrons, which are all negative, will redistribute evenly, right? The electrostatic force has an equation that is like a similar format to gravity, the big gravity equation. Electrostatic force, if you look at page, I think it's page 4 of your reference table. It's the section with electricity. You should see an equation that looks like this, right? And this equation describes how you can actually calculate how big is the force of attraction between those things, how big is the force of repulsion between those things, right? What does all of this nonsense stand for? K is the electrostatic constant. If I could spell. There we go. It is on the reference table. It's something that you don't need to memorize. It's super big. Numerically, 8.99 times 10 to the 9th. 99% sure of that. I'm going to make a comparison to gravity in a second. Q is the charge. I want you to remember something about charge. It could be positive or negative, right? If one charge is positive and one charge is negative, positive times negative is going to be a negative number. Your force is going to be negative. Hopefully earlier in the year you remember me saying that forces are pushes or pulls. Generally we say that pushes are positive forces and that pulling something is a negative force. Positive and negative will make a negative force. They will pull towards each other. That's attraction. If they are both positive, the force, the electrostatic force, is positive, numerically, which means that they push apart. If they're both negative, negative times negative makes a positive. So, 2 negative charges will result in a positive electrostatic force, which means they will repel, right? And then R is the distance between charges. All right, so how far apart are they? The electrostatic force will get bigger if you increase the amount of charge present, or you bring them closer together. This is really similar. This equation should look really similar to the big force of gravity equation, which was G m1 m2 over r squared. Right? The difference is that G was 6.67 times 10 to the negative 11th. So look at how big or how small this is compared to K. It's 20 orders of magnitude bigger, which is 20 zeros bigger. This is why you can roll a balloon on your head, stick it to the wall, and it'll stay there for a while. The electrostatic force between charges is not 20 times stronger on a base level than the force of gravity. It's 20 zeros stronger on a base level than the force of gravity. And this is why stray charges are generally dangerous, right? Because they give off such strong forces, they can be dangerous. which is why lightning is dangerous, which is why a big static discharge is dangerous in electronic devices, because it has a lot of force and it carries a lot of energy. They go hand in hand, right? We'll talk about that soon. If you look at the that excuse me, if you look at that electricity section, you'll notice. It's not the Rona. I just like am bad at breathing. Okay, sorry. But because it's why if you're working with electronic stuff, you're supposed to be grounded. You're supposed to make a way so that you cannot be charged while you're contacting all of this like metal stuff that's a really good conductor. So this equation, right? Using this equation to solve for electrostatic force, using this concept of how if you bring a charged object near an uncharged one, it will push negative charges away or it will pull negative charges towards it. And there's a little bit more to talk about here, but the two things that I'll focus on for the quiz, it'll be a fairly short quiz, are really this equation, right? The electrostatic force equation, the concept of things repelling and attracting, the concept of why neutral things will attract, and the concept of, just on a baseline, like static electricity, right? How does static electricity function? Why does static electricity happen? It's because charges build up in one place, right? Oh, you know what? Okay, there is one last thing with respect to this. I'm gonna say something here. I'm gonna make an example very quickly here. And again, there are gonna be questions that go up as an assignment. They'll probably go up like on B day, and they'll be due like on C day. So hopefully you're watching this after B day and before C day. I'll put out an announcement at the beginning of, I'll put out an announcement. So the last thing that I want to talk about is, let's say that I have this object, which has a net charge of +3. So it just happens to have 3 extra positive charges on it. And I also have this object, which has a net positive charge of +1. So this thing has Q equals +3. This thing has Q equals +1. Right? What will they do to each other? Well, they will repel. Okay, cool. Oh, yeah, I'll bring units into the fray with the... No, I'll bring them into the fray right now. Charge is measured in a unit that is abbreviated by a capital C. It's the coulomb. So charge... The charge unit, the unit for charges, is the coulomb, or a capital C. So generally when you look at questions like this, you'll see this Q is +3 and the other Q is +1. These two objects will repel each other. If I told you how far apart they were, let's say that they were 0.5 meters apart, then you could solve for an electrostatic force, because you have the two Q's, you have the distance between them, and you have the electrostatic constant. But that's not what I'm going to talk about here. What I'm going to talk about is what happens if I take these two charged objects, I touch them together, and then I take them apart from each other. All right? What's going to happen with two objects is the charge will be conserved. I'm not going to gain or lose charge. However, if touched together, charged objects will try to distribute total charge evenly. Now, if it's not possible to distribute it evenly, then it will distribute as evenly as it can. But let's say that you can only do things in terms of whole coulombs. Well, that means that if I take these two objects with a net charge, the total charge is +4, I take them, I touch them together, I take them apart. Then after I separate them, the one on the left will be +2, the one on the right will be +2. right? So this is conservation of charge. And this is what happens if you actually take a charged object and touch it to a neutral object. You'll now have two charged objects, each having half the original charge of your single charged object. If you have two charged objects and you touch them together and then take them apart, whatever the total charge was, they will redistribute as evenly as possible. If I had a +3 and a -3, and I put them together and take them apart, each of them would be 0. If I had a +2 and a -1, and I put them together, they would both try to be like 1.5, if that's possible. But any combination that added up to +2 -1 is a total of +1. So, oh, sorry. So it should have been just 1 each. Or no, half each. It would have been half each. But whatever the total charge divided by 2, is what it would try to do. If it can't do that, any combination of charges that adds up to the total charge will work. So with +2 -1, that's a total charge of +1. Any two charges that add up to +1. Technically, if you put them together, you could end up with +4 and -3. It still adds up to +1. I haven't violated conservation of charge. It's the same net charge present before and after. Somehow things just got more extreme. That's not typically what happens, but it could. All right? So 3 concepts on the quiz. What happens to charged objects if you bring them together and touch them and take them apart? How can you solve for the electrostatic force on charged objects? And what happens to charged objects or neutral objects when you bring them near each other? What interaction will you find? All right. I know that was a lot. I guess this is what we'll be doing on C-Day, because we'll finish the lab. So, or we finished stuff. So I'm doing things a little ahead of time, and we'll see how that works out. I might be getting a little too ahead of myself, but remember that there will be a quiz on Friday. Again, regardless of letter day. Remember that it's only on the concepts that were here, and make sure to take pictures and turn in the lab to the appropriate assignments. They are online. I'm not gonna... I sort of, like, walked around and looked and saw who was doing what, but I'd also like a physical record of it. I know that you've done it, right? That's mostly for remote students. Please take pictures of your work and submit them online, all right? Until the next class, or until the next video, I will see y'all. Take care, kids. Be good, be safe, and see you next time.